Have you ever wondered if given the chance, where or when you would travel to? This question, as simple as it may seem, has captivated the minds of humanity for centuries. The concept of time travel, of stepping outside the relentless march of seconds, minutes and hours, is a universal fascination that transcends boundaries and cultures. From the whimsical pages of H.G. Wells' The Time Machine to the mind-bending paradoxes presented in blockbuster films like Back to the Future, time travel has been a cornerstone of pop culture and literature, a topic that has sparked the imagination of thinkers, dreamers, and even scientists alike. Its allure lies in its blend of the impossible and the profoundly human desire to explore, to understand, to make sense of the world and our place within it. But what exactly is time travel? And could it be more than just a figment of our imagination? Time travel isn't a modern concept, it has roots that dig deep into our past. Traces of time travel are found in ancient mythology and folklore. In Hindu mythology, the epic Mahabharata mentions King Raivatakakudmi, who travels to heaven to meet the creator, Brahma, only to return to earth to find many ages have passed in his absence. A similar tale is found in Japanese folklore, where a fisherman named Urashima Taro visits an underwater palace and returns after 3 days, only to discover 300 years have slipped by in the human world. These stories, while fantastical, hint at the concept of time travel, a testament to our ancestors' fascination with the passage of time. However, it wasn't until the 19th century that time travel began to evolve from a concept of myth and legend into a scientific theory. In the late 19th century, H.G. Wells' novel, The Time Machine, presented the idea of a vehicle that could carry its occupant through time. Wells's work, though fictional, was pivotal in shifting the public's perception of time travel from pure fantasy to a theoretical possibility. The real scientific breakthrough, however, came in the early 20th century with Albert Einstein's theory of relativity. Einstein's groundbreaking work suggested that time and space are interwoven into a single continuum known as space-time. His theory proposed that the speed of light is constant for all observers, but time itself can slow down or speed up depending on the speed of the observer. This was a revolutionary concept, suggesting that time travel might not just be possible, but a natural consequence of the laws of physics. In the decades since Einstein, physicists have continued to explore the concept of time travel, each new theory adding layers of complexity and intrigue to our understanding of the universe. So, as we can see, time travel has always been a part of our collective consciousness, evolving alongside our understanding of the universe. As we delve deeper into the mysteries of space and time, who knows what future discoveries might further evolve our understanding of time travel? But how might time travel work in a practical sense, you might ask? Let's dive into some popular theories that try to answer precisely that. Firstly, we have the concept of wormholes. Envision a wormhole as a kind of tunnel with two ends, each at separate points in space and time. Theoretically, if one could create, maintain, and traverse such a wormhole, it could provide a shortcut through both space and time. However, it's important to note that wormholes are purely theoretical at this point, with no empirical evidence to back their existence. Then we have the idea of faster-than-light travel. According to Einstein's theory of relativity, as an object approaches the speed of light, time for that object slows down relative to the rest of the universe. So if one could somehow surpass the speed of light, could they not also surpass time itself? The catch here is that, as far as we know, nothing can exceed the speed of light. It's the cosmic speed limit that keeps time travel in the realm of science fiction. Lastly, we have the concept of bending space-time. This idea is rooted in the understanding that space and time are interconnected, forming a four-dimensional fabric known as space-time. Large objects like planets and stars cause this fabric to curve, creating what we perceive as gravity. If we could manipulate this curvature, could we not also manipulate time? This is a tantalizing theory, but one that currently lies beyond our technological capabilities. While these theories might seem far-fetched, they are the result of serious scientific inquiry. It's worth remembering that many scientific realities of today, such as the existence of atoms or the fact that the Earth orbits the Sun, were once considered as fanciful as time travel is now. So who knows what the future might hold? Maybe one day we'll look back at this very moment from the future. Now, wouldn't that be something? Time travel isn't without its complications, however. Indeed, the concept of time travel, as intriguing as it is, opens the door to a labyrinth of paradoxes that challenge our understanding of reality. Let's delve into a couple of these mind-bending paradoxes, starting with the notorious grandfather paradox. Imagine this scenario. You've invented a time machine and you decide to visit the past. Once there, you inadvertently cause the death of your grandfather before he meets your grandmother. This creates a paradox. If your grandfather died before he met your grandmother, your parent, and consequently you, should never have been born. But if you were never born, then who travelled back in time and caused your grandfather's demise? This is the essence of the grandfather paradox, a classic example of the causal loops that can arise with time travel. But the paradoxes don't stop there. Let's move on to another paradox known as the bootstrap paradox, also referred to as a causal loop. This paradox involves an object or piece of information that is sent back in time, creating a loop in which the object or information has no discernible origin. Consider this: you're a scientist in the future who receives a detailed blueprint of a time machine from your past self. You build the time machine based on these blueprints, and once it's done, you send the same blueprints back to your past self. So the question arises: who originally created these blueprints? This paradox illustrates the complexities of cause and effect in time travel. These paradoxes, the grandfather and the bootstrap, are just two examples from the myriad of paradoxes that arise from the concept of time travel. They challenge our understanding of causality and the nature of time itself, presenting a seemingly impossible scenario. These paradoxes present real challenges to the concept of time travel, making it a complex and fascinating subject to explore. And so, our journey into the mind-bending world of time travel continues. While time travel remains a theoretical concept, there have been real-world experiments that hint at its potential reality. In the realm of scientific exploration, one of the most intriguing experiments that could potentially support the concept of time travel is the Haefel-Keating experiment. In the early 70s, scientists Joseph Haefel and Richard Keating embarked on an experiment that involved atomic clocks and commercial planes. They placed atomic clocks, known for their precise timekeeping, on commercial flights that circled the globe both eastward and westward. What they found was astonishing. The clocks on the planes showed a different time compared to the ones left at the sea level. This experiment provided a practical confirmation of Einstein's theory of relativity, which suggests that time can be affected by speed and gravity. So how does this relate to time travel? Well, it all comes down to the concept of time dilation. Time dilation is a difference in the elapsed time measured by two observers, due to a relative velocity between them or to a difference in gravitational potential between their locations. In simpler terms, it means that time can appear to move slower or faster, depending on how fast you're moving or where you are in relation to a gravitational field. This is where our astronauts come into play. Astronauts in space experience time slightly differently than we do on Earth. Due to the weaker gravitational field in space compared to Earth, time actually passes faster for them. It's a minuscule difference, but it's a difference nonetheless. Now, this doesn't mean we'll be pulling a Marty McFly and zipping back to the 50s in a DeLorean, but it does suggest that time isn't as rigid and unyielding as we might think. Our understanding of time and the possibility of manipulating it is still in its infancy. So, while we may not be hopping in a time machine anytime soon, the concept of time travel isn't as far-fetched as it might initially seem. As we continue to push the boundaries of science and technology, who knows what fascinating discoveries lie just beyond the horizon? So, we've taken quite a journey through time ourselves, haven't we? We embarked on an exploration into the enigma of time travel, starting with its conceptual evolution. We learned how the idea of time travel has evolved and transformed from ancient myths and legends to modern scientific theories. We then delved into the mechanics of time travel, looking at the science behind theoretical concepts like wormholes and time dilation. The paradoxes associated with time travel were also discussed, challenging our conventional understanding of causality and the flow of time. Lastly, we examined the possibility of time travel in reality. As we've seen, while the idea is captivating, it is also fraught with complexities and contradictions. Nevertheless, it offers a fascinating perspective into our understanding of the universe and our place within it. Whether time travel ever becomes a reality or remains in the realm of science fiction, It is undoubtedly a concept that will continue to fascinate us for generations to come.